Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
I want you to do something for me right now. If you're driving, obviously keep your hands on the wheel, but if you're not, if you're sitting at a desk or on a couch, just reach out and touch the nearest solid object.
Yeah, maybe it's your desk.
Could be your desk, maybe the fabric on your chair.
Or even just, clap your hands together. Feel that.
Exactly. Feel that resistance, that solidity. It feels real, right? I mean, it feels like it occupies space. It has depth. It has volume.
Mm-hmm.
You can move your hand through the air, up, down, left, right, forward, back. I mean, we live in a world of three dimensions.
Yeah.
That feels like the most fundamental fact of our existence.
It really does. It's the stage, right? The stage where our entire lives play out.
Yeah.
We're 3D creatures. We navigate a 3D world.
Right, but here's the hook, and I'm going to warn you, this is the kind of idea that might make you want to pull the car over or, I don't know, just stare at your hands for an hour.
Uh-huh.
What if I told you that this feeling of depth, this whole sensation of space that we're moving through is a lie?
Well, lie might be a strong word. Let's maybe call it a compelling illusion.
Okay, a very convincing illusion. What if everything in our universe, gravity, matter, time, the very space between you and me right now, what if it's all just a projection?
Right.
Like we are all just encoded data, just smeared across some distant two-dimensional surface at the edge of the cosmos.
It sounds like the plot of a sci-fi novel.
Right.
Or, something you'd hear in a college dorm room at 3 a.m.
Right.
But what you're describing is actually one of the most robust, heavily researched, and mathematically significant concepts in modern theoretical physics.
We are talking about the holographic principle. And I have to admit, when I first saw this topic come up, I thought, okay, we're finally doing the simulation theory episode. We're doing the Matrix.
Yeah, right.
But this isn't that, is it? It's different.
It touches on similar themes, for sure.
Yeah.
But no, this isn't about evil robots using us as batteries. This is about the fundamental architecture of reality itself. It's about how the universe stores information.
And the implications are, they're unsettling.
To say the least. It challenges everything we think we know about where we are.
So before we get into the heavy math, and we will, but we'll try to keep it painless, let's just define the core concept. When we say holographic principle, what are we actually claiming?
The core claim is this. All of the information that's contained in a volume of space, so imagine a room, a planet, or the entire universe, all of it can be completely, 100% described by data that lives on the boundary of that region.
A boundary, like the shell.
Right.
The surface area.
So to use the analogy that gives this principle its name,
yeah,
it's like a hologram.
Yeah.
But I feel like we have to be careful with that word because when I hear hologram, I think of, Tupac at Coachella.
Right.
I think of a ghost shimmering on a stage.
And that's a visual trick using mirrors and light. It's not quite the physics definition. A better way to think about it is the security sticker on your credit card.
Oh, the little shiny bird or the globe. Exactly. Now, if you run your finger over that sticker, what do you feel?
It's flat. It's just a piece of plastic. It's two-dimensional.
Precisely. The physical object is 2D. But when light hits it, what do you see?
You see depth. You see a little bird floating in 3D space. You can tilt the card and sort of see the side of it.
Right. The reality of the image looks three-dimensional, but all the information that generates that image is just etched onto a flat two-dimensional surface.
And the holographic principle is suggesting that the entire universe might be that credit card sticker.
In a manner of speaking, yeah. The theory suggests that the three-dimensional world we inhabit, the bulk, as physicists call it, is a projection of fundamental quantum information that's stored on a lower dimensional boundary.
Which would mean that space isn't even a fundamental thing. It's just emergent.
It is.
Like a user interface on a computer screen.
That is the implication. And it forces us to ask whether here, this room, this planet is really here, or if the real physics is happening somewhere else, on the edge of the cosmos.
Okay, my brain is already starting to itch, that's usually a good sign. We have a massive roadmap ahead of us here. We need to understand where this idea even came from, which strangely enough wasn't from studying holograms. It was from studying black holes.
Black holes are the key to this entire story. They always are.
And we're going to have to unpack something called the Maldacena conjecture, which it sounds like a Robert Ludlum thriller, but it's actually the Rosetta Stone for this whole theory.
It absolutely is.
We're going to talk about the information paradox, the sort of crime scene that started this whole investigation.
And we'll get into how this actually solves some of the biggest problems in physics.
And then, because we can't help ourselves, we're going to get into the really wild stuff. Quantum computing, the nature of consciousness, and whether our universe is actually just a big error-correcting code.
It's a fascinating journey. It connects the largest things in the universe, black holes, with the smallest things imaginable, quantum bits.
So let's start at the beginning, or I guess let's start in the 1990s, because this theory didn't just prop out of nowhere. It came from a crisis, right?
It did. It came from a conflict. You have to understand, in physics, we basically have two main rule books. We have general relativity, Einstein's masterpiece. It describes big things. Gravity, stars, galaxies, the shape of space.
And then we have quantum mechanics,
which describes the small things. Atoms, particles, information. And usually these two rule books, they just ignore each other. They stay in their own lanes. But in a black hole,
they crash.
They crash hard. In a black hole, you have a massive amount of gravity. That's general relativity, cracking things down to a tiny microscopic point. That's quantum mechanics.
So you have to use both rule books at the same time.
You have to. And when physicists tried to do that back in the 90s, the math just started screaming at them.
And they were specifically looking at entropy, right? Now, entropy is one of those words that gets thrown around a lot. Usually people say it means disorder, like my messy desk has high entropy.
That's the casual definition, yeah. But in information theory, entropy is much more precise. It's a measure of hidden information. It's the number of distinct microstates or configurations that a system can have.
Okay, let's dumb that down a little. Microstates.
Think of it as the number of yes-no questions you'd need to ask to fully describe a system down to the very last atom. It's a measure of how much data is inside.
Got it. So let's talk about a library. I love libraries. If I want to know how much information fits in a library, what do I look at?
Well, intuitively, you'd look at the volume of the room, the size of the space inside.
Right. If I have a library that's, say, 1,000 cubic feet, I can fit X number of books. If I build a new library that is 2,000 cubic feet, double the volume, I can fit double the books.
Exactly. That's our common sense. It's called extensive scaling. The amount of stuff you can pack into a region depends on the volume of that region. It's cubed.
It's cubed.
Right. If you double the radius of a sphere, the volume goes up by a factor of 8. So you should be able to fit 8 times as much information inside.
Right. Because we live in a 3D world, we should be able to stack data in 3D. We should be able to fill every little cubic inch of space with a hard drive or something.
That is what everyone assumed, until they looked at black holes.
And this is where Gerard Hooft and Leonard Susskind come in.
The fathers of the holographic principle. They, along with Jacob Bekenstein before them, realized something that it violated all that common sense. They found that if you want to measure the maximum amount of entropy, the maximum amount of information you can stuff into a region of space, you don't look at the volume.
You don't.
No, you look at the surface area.
Wait, hold on. So it doesn't matter how big the inside is. It only matters how much surface area the skin has.
Correct. The limit on information isn't cubic. It's squared.
So back to the library.
Okay, back to the library. Imagine you're trying to pack it with books. You just keep shoving books in. Eventually, gravity takes over, and that library collapses into a black hole.
Okay, so now I have a black hole library. Great.
Right. And if you calculate how much information is hidden inside that black hole, the math tells you, do not count the interior. Count the square inches of the event horizon. The capacity is determined by the walls, not by the room.
That feels wrong. That feels deeply, fundamentally wrong.
It feels wrong because it violates our entire intuition about dimensions. I mean, think about it this way. Imagine you have a box of ping pong balls. You want to know how many balls fit in the box. You'd assume it depends on how deep the box is, right?
Yeah, of course. I can stack them. Layers and layers of balls.
But the black hole math says no. The maximum number of balls you can fit is actually determined by how many circles you can draw on the lid of the box.
So if I make the box deeper, but I keep the lid the same size, I can't add any more balls?
Effectively, yeah. If you try to add more, the physics breaks. The region would have to collapse or expand. The limit is always the surface area. This was known as the Bekenstein bound.
The Bekenstein bound. It really does sound like a spy movie title. The Bekenstein bound.
Apples. It is one of the most profound discoveries in physics. It tells us that the resolution of the universe is finite. And more importantly, it suggests that the fundamental pixels of reality, the smallest possible units of information, are tiling the surface, not filling the volume.
Let's pause on that pixel idea for a second, because if we're talking about a 3D world, we'd usually talk about voxels, right? 3D pixels.
Like in Minecraft, yeah.
Exactly. Everything is made of little cubes.
Right. If the universe were truly fundamentally 3D all the way down, it would be made of voxels.
Yeah.
But the Bekenstein bound says that at the most fundamental level, the Planck scale, the universe behaves like it's made of pixels on a 2D sheet.
So this was the first breadcrumb, the universe sort of whispering to us, hey, you think the important stuff is inside the volume, but the accounting, the real ledger, is kept on the walls.
Exactly. And if the maximum amount of information in any volume of space is determined by its boundary, then maybe, just maybe, the interior isn't the fundamental thing. Maybe the interior is just a projection of the data on the boundary.
It's like discovering that the book you're reading isn't a story about a world, but just a really, really complex index for that world.
Or that the room you're standing in is just a very convincing hologram.
Yeah.
But for a few years, this was just a weird observation about black holes. It was a suspicion. It wasn't a full-blown theory.
Until 1997.
Until 1997.
Enter Juan Maldacena.
The man who changed everything.
So Maldacena comes along, and he doesn't just say, hey, maybe the universe is a hologram. He actually builds a mathematical model that shows it works.
He provided the first concrete mathematical realization of the holographic principle. It's called the AD-CFT correspondence.
Okay, AD-SCFT. I see this acronym everywhere in the research. It looks like a license plate number, or maybe a bad Wi-Fi password.
Chuckles. It's certainly a mouthful. Most physicists just call it the Maldacena conjecture, or sometimes just the duality.
We need to unpack this, because all the sources say this is the Rosetta Stone. If we can get our heads around this, we get the whole theory. So let's break it down. AD-S, anti-de Sitter space.
All right, so AD-S refers to the bulk, the inside of things.
Anti-de Sitter. Sounds like a villain. I am anti-de Sitter.
It does sound a bit ominous.
Yeah.
But it just describes the specific geometry of space. Now, I'm going to need you to do some mental gymnastics with me here.
Yeah.
Forget our universe for a second. Forget the expanding cosmos we see through telescopes. Maldacena built a toy universe, a model.
Okay, I'm with you. I'm in the toy universe. What's it like?
Imagine a can of soup.
A can of soup. Okay.
Simple can of soup.
Exactly.
The AD-S part, the anti-de Sitter space, that's the soup. It's the volume inside the can. It has 3 dimensions, height, width, depth. It has gravity. It has little black holes floating around in the broth. It has stars. It's a dynamic 3D world.
Okay. So I'm swimming in the soup. I feel gravity. I see 3D objects. All good.
Exactly. Now, there's one very weird thing about this soup. It has what we call negative curvature.
Negative curvature. What does that mean visually? What does that look like?
Have you ever seen those Escher drawings? The circle limit ones with the angels and demons?
Yes, where they're all interlocking, and as they get closer to the edge of the circle, they get smaller and smaller and smaller.
And they seem to go on forever towards the edge, but they never quite touch it.
Right.
That is a 2D representation of hyperbolic geometry or negative curvature. In anti-de Sitter space, space itself is warped like that, like a funhouse mirror version of a universe. But the key thing is, it has a boundary. It has an edge.
The label on the soup can.
The label on the soup can. That is the boundary. And that brings us to the second half of the acronym, CFT.
Conformal field theory.
Right? This is the theory that lives on the label. Now, here's the crucial difference. The soup, the AD-S space, has gravity. The label, the CFT, does not have gravity.
No gravity on the label.
None whatsoever. It is just a flat surface with quantum particles buzzing around, interacting with each other. It's a standard quantum field theory, like the ones we use to describe electromagnetism.
So we have 2 totally different worlds here. We have the soup, 3D gravity black holes, and we have the label, 2D, no gravity, just particles.
And here is Maldacena's genius. He proved mathematically that these 2 theories are equivalent. They are duals of each other.
Equivalent. How can a 3D gravitational world be equivalent to a 2D flat one?
It means that every single thing that happens in the soup has a direct, perfect translation to something happening on the label.
So if I drop a little rock into the soup,
that corresponds to a specific ripple of particles on the label.
and if a black hole forms in the soup,
That corresponds to a specific temperature rising in the particles on the label, a specific thermal state.
so it's a dictionary.
It is a perfect dictionary. You can translate any sentence from soup language, which is gravity, into label language, which is quantum fields. And this is why physicists went absolutely nuts for it. Because sometimes the math in the soup is just It's impossible.
Gravity's hard.
Gravity's notoriously hard. The equations get incredibly messy.
Yeah.
But using the dictionary, you can translate that hard gravity problem onto the label. Suddenly it becomes a quantum particle problem, which might be much easier to solve.
Oh, wow.
You solve it there, get the answer, and then you translate it back to the soup.
It's a cheat code.
It is the ultimate cheat code for physics. It's a concept called strong-weak duality. When gravity is strong and complicated in the bulk, the interactions on the boundary are simple and weak, and vice versa.
So even if the holographic principle isn't real in some philosophical sense, even if we weren't literally living on a wall, this tool is so useful that physicists use it every day.
Oh, absolutely. It has revolutionized string theory, nuclear physics, condensed matter physics, and it's a workhorse. But the question we are asking today isn't just, is it useful? It's, is it true?
Right. Is the soup real or is the label real?
Exactly.
Because if Maldacena is right and the boundary contains all the information of the bulk, then the bulk is technically redundant. You don't need the 3D space to explain the universe. The 2D space on the label does it perfectly well.
That's the existential crisis right there. If the 2D theory is complete, then the 3D world is just a projection. It's an emergent phenomenon, a hologram.
I need to sit with the soup cam universe for a second. Because this model, this duality, it actually helped solve a crime, a cosmic crime involving Stephen Hawking.
The information paradox.
The information paradox. This is the Sherlock Holmes moment of the whole story. Because for a long time, physics had this gaping hole in it, a murder mystery where the victim was information itself.
And Stephen Hawking was the prime suspect.
Set the scene for us. What did Hawking do?
Well, back in the 70s, Hawking made a startling discovery about black holes. Before him, we thought black holes were just these eternal prisons. Nothing ever gets out.
The ultimate Roach Motel? Things check in.
But they don't check out.
Right.
But Hawking applied quantum mechanics to the very edge of the black hole, the event horizon. And he realized that due to quantum fluctuations, black holes should actually emit radiation. They should glow very faintly.
This is Hawking radiation. How does that work?
Very briefly. Okay, very briefly. In empty quantum space, pairs of virtual particles are constantly popping into existence, a particle and an antiparticle. Usually, they just annihilate each other and vanish. But if they pop up right on the edge of a black hole,
one falls in,
and the other one escapes. The one that escapes becomes real radiation. The one that falls in effectively subtracts a tiny bit of energy from the black hole.
So the black hole is losing weight. It's on a diet.
A very, very slow diet. And if you wait long enough, trillions and trillions and trillions of years, the black hole will radiate away all of its mass and poof, disappear.
Okay. The black hole dies. Why is that a paradox? Why is that a crisis for physics?
Because of what fell inside.
Yeah.
Imagine you take your diary. It has your secrets, your memories, all this unique information. You throw it into a black hole.
Bye-bye, diary. My secrets are safe.
Now, you wait 1 trillion years. The black hole evaporates. It turns into this Hawking radiation. But here's the thing. Hawking's calculations showed that this radiation is random. It's thermal. It's just heat. It doesn't contain the text of your diary.
The diary just gone.
If the black hole disappears and the radiation coming out doesn't have the data, then yes, the information has been permanently deleted from the universe.
And I'm guessing physicists don't like deleting things.
They hate it. It breaks a fundamental rule of quantum mechanics called unitarity. In quantum mechanics, information is immortal. You can scramble it like you could burn a book into ash. But in principle, if you collected all the ash and smoke and light, you could reconstruct the book. Information is never truly lost.
But Hawking was saying, nope, in a black hole, it always lost.
Exactly. He said black holes are cosmic erasers. And if that's true, then quantum mechanics is wrong. Physics is broken. The past doesn't determine the future. It was a complete disaster.
It was the black hole war. Susskind versus Hawking?
For decades, nobody knew who was right until the holographic principle came in as the peacekeeper.
So how does the hologram save the diary?
Remember the soup can? Remember the duality? The 3D black hole in the soup where the diary fell in is completely equivalent to the 2D label, the quantum field theory. We know for a fact, with 100% certainty, that the theory on the label is unitary. It never, ever loses information. It's a standard quantum system. It plays by the rules.
So if the label can't possibly lose the diary,
then the soup can't lose it either. Because they are the same system, just viewed in two different ways, the information must be preserved.
So Hawking was wrong.
He eventually conceded. He famously admitted he was wrong. The consensus now is that the information isn't lost. It gets encoded into the outgoing radiation in a highly complex, scrambled way.
So the diary doesn't disappear. It just gets turned into the most complicated barcode in the entire universe.
That's a perfect way to put it. From the perspective of the holographic principle, the information that falls into the black hole is effectively smeared out and stored on the boundary. It never truly leaves the system.
That is a relief, I guess. I mean, I don't want my diary read, but I definitely don't want it to break all the laws of physics.
Apples. It saves physics, yeah, but it does so at a cost. And the cost is accepting that location is an illusion. The diary isn't really inside the hole. It's painted on the horizon.
And this leads us to the part of the whole discussion that I find the most mind-bending. Because if the boundary is the thing that follows the rules and the bulk is the thing that gives us illusions, then space itself isn't real.
Space is emergent. That is the phrase you'll hear physicists use over and over.
Emergent. Okay, let's unpack that word.
Think about wetness. You have a single water molecule. Is that molecule wet?
No, it's just H2O. It's just hydrogen and oxygen atoms.
Wetness is a property that emerges when you have billions and billions of them all sloshing around together. Or think about heat. Heat isn't a thing in itself. It's just the average motion of atoms.
So you're saying space, the distance between my nose and this microphone, is like heat. It's not a fundamental thing. It's just what happens when what happens?
When quantum information gets entangled.
Entanglement. The spooky action at a distance.
Yes. There is a growing movement in physics, an idea called it from qubit. The idea is that the fundamental building block of reality is the qubit, a unit of quantum information. And space is the geometry that emerges from the entanglement of those qubits.
Explain that to me. How does entanglement create distance?
Okay, so imagine 2 points on the boundary on our soup can label. If the information at those 2 points is highly entangled, meaning their quantum states are deeply linked, they effectively pull the corresponding regions in the bulk together. They create a sort of shortcut through the bulk.
A wormhole.
It's called an Einstein-Rosen bridge, or wormhole, yes. And that shortcut is what we perceive as closeness.
So I am sitting next to you right now, not because we're physically close in some fundamental container, but because the qubits that represent us on the boundary are really, really entangled.
That's the hypothesis. Distance is a measure of entanglement. If you could somehow cut the entanglement between 2 regions on the boundary, the space between them in the bulk would literally snap.
Yeah.
The geometry would fall apart.
That is a terrifying thought. It means the fabric of reality is just. It's just correlations in data.
It leads to this concept called entanglement wedges.
Which sounds like a terrible appetizer at a restaurant.
Shuckles, I'll have the entanglement wedges with a side of quantum ranch.
No, it just means that specific chunks of space-time, specific wedges of the bulk, are generated by specific corresponding chunks of data on the boundary. You can map exactly which part of the hologram is responsible for creating which part of the room you're in.
This makes me think of a video game. I play a lot of these big open-world games.
That's a perfect analogy.
When I'm playing, I see a mountain way off in the distance. I can walk to it. It feels like 3D space. But in reality, on the hard drive, the data for Mountain A and Mountain B might be on completely different sectors of the disk. They aren't next to each other on the chip at all.
Exactly. They are linked by pointers, by code.
So the 3D world of the game is emergent. It's being rendered in real time. Precisely. The 2D surface of the ship is the reality. The 3D world of the game is the projection. And just like in a game, if the code gets corrupted, the mountain might just disappear, or the ground might fall out from under you.
So we're Sims. We're just very, very high-resolution Sims.
We might be. But instead of a hard drive, the chip is the boundary of the universe, and the code is quantum entanglement.
Okay, so if we accept this, that we are in the rendered environment, we have to ask about the hardware. We talked about the soup can universe, but as you mentioned, that was a toy universe.
Right, the anti-de Sitter space.
But we don't live in a soup can. Our universe is expanding.
We live in what's called de Sitter space, or something very close to it. It has a positive curvature.
So does any of this actually apply to us? Or is this just a really cool theory for a universe that doesn't actually exist?
This is the biggest criticism. This is the Achilles heel of the theory right now. The math works beautifully and perfectly in the soup can, in at-s space. It is much, much harder to make it work in our universe in de Sitter space.
Why? What's the main difference?
The boundary. In the soup can, the boundary is a clear, hard wall. It acts like a perfect mirror. Light hits it and bounces back in. A perfect static container. In our universe, Well, we're expanding. We don't have a hard wall at the edge.
So where is our label? Where is our screen?
That's the multi-trillion-dollar question. Some physicists think the screen might be the cosmic horizon.
The edge of the observable universe.
Right. If you look as far as you can in any direction, you eventually hit a point where light from beyond hasn't had time to reach us yet. That horizon surrounds us. Some propose that this horizon could act as our holographic screen.
So the edge of what we can see is the hard drive, and everything inside, all the galaxies, stars, us, is the projection inward from that screen.
That is one possibility. It's a model called DSCFT, de Sitter CFT, but the math is much, much messier. However, the Bekenstein bound, that fundamental limit on entropy, it seems to hold true regardless of the shape of the universe. So the core principle is likely correct, even if the screen is harder for us to define.
This actually touches on something else I saw in the research quantum computing. I saw a note about error-correcting codes, and this felt like the most sci-fi part of all of this.
It's also the most practical tech part. It turns out the mathematics that makes the holographic principle work is essentially identical to the math we are now using to build fault-tolerant quantum computers.
Explain that connection. What is an error-correcting code?
Okay, imagine you have an old DVD. Remember DVDs?
I'm old enough to remember, yes.
If you get a little scratch on a DVD, does the movie stop working?
Usually no,
Right.
unless it's a really deep scratch. It might skip for a second, but it plays through.
And why is that? It's because the data on the DVD is redundant. The information for a specific frame of the movie isn't just in one tiny spot, it's spread out. It's encoded in a way that allows the player to fill in the blanks if some of the data is missing.
Redundancy.
Exactly. Logical redundancy. Now, think about the hologram. The information about a single point in the bulk, say a star in the middle of the soup, is spread out all across the boundary. It's smeared out.
So the star isn't just here on one spot of the boundary, it's encoded everywhere on the boundary.
In a sense, yes. And this is crucial for quantum computers. Quantum data, qubits, they're incredibly fragile. If a stray atom or a bit of radiation hits your qubit, the data can be lost. So you have to use these error-correcting codes to spread that single piece of logical data out across many physical qubits. If one gets corrupted, the others can reconstruct the whole.
And the universe is doing this.
The math suggests the universe is this. The holographic principle acts like a giant natural error-correcting code.
So space is robust because it's redundant.
Yes. If you were to somehow scratch the boundary, if you deleted a chunk of the label, you could still reconstruct the soup in the middle. The bulk is protected by this holographic redundancy.
That is weirdly comforting and also deeply terrifying. It implies the universe is somehow engineered to preserve information.
Or that stability itself requires this structure. A universe that wasn't holographic, that didn't have this built-in error correction, might just collapse. Space might just dissolve into nothing. We might be here because the universe is a hologram.
We are the glitch-proof simulation. I like the sound of that.
I wouldn't go quite that far, but the parallel is definitely undeniable.
Okay, I want to push into the deep end of the pool for a minute, the speculative territory. Because if we are talking about information and error correction and projections, we have to talk about consciousness.
Ah, the C word. Physicists usually hate touching this, but let's do it.
The sources mentioned it, even just briefly. If reality is emergent, if 3D space is just what happens when 2D information gets processed in a certain way, does that mean our brains are doing the processing? Are we creating it?
Well, there is the whole question of the observer. In quantum mechanics, the observer is key. In a hologram, you need a light source, a laser, to shine through the film to create the 3D image.
So he is shining the light.
That's the mystical question.
Yeah.
But from a more grounded neuroscience perspective, some people ask, is consciousness just a very high level of information integration? If the universe is built on it from qubit, is our consciousness just a particularly complex knot of those qubits processing themselves?
And what about AI? We're building these massive neural networks now.
This is where it gets really fun and really speculative. If 3D space emerges from the processing of information, could a sufficiently complex AI develop its own space?
Whoa.
If an AI becomes complex enough, if its internal data becomes entangled enough, could a new dimension emerge inside the AI that we can't see or access?
Like it perceives a spatial reality that only exists within its own code.
Exactly. Just like our spatial reality might just exist within the code that's written on the boundary of the universe. We might be the AI living in the simulation that's being run by the boundary of physics.
Okay, that gives me chills. That is a Black Mirror episode waiting to happen.
It is highly, highly speculative. We have zero proof of this. But the holographic principle opens the door to these kinds of questions because it reduces physics down to information. And information is something we are finally learning to manipulate ourselves.
Before we completely float away into the ether here, let's ground this again. We have to be honest with everyone listening. Is this theory true with a capital T?
That is a very complicated question.
Because there are critics. It's not universally accepted.
There are, and the biggest criticism is what you could call the math trick argument.
The idea that it's just a useful calculator, not a description of reality.
Right. Just because the math allows you to translate the soup to the label doesn't necessarily mean the label is more real.
A map of New York is incredibly useful. I can use it to find my way around, but the map isn't the city.
That's the argument. Some physicists argue that the duality is just a powerful relationship between two mathematical structures. It doesn't mean we physically live on a wall. It just means the wall describes us perfectly.
But does the distinction even matter? If the description is perfect, if you can predict every single move I make by just looking at the wall, am I not, for all intents and purposes, on the wall?
That's the philosophical counterargument. If it walks like a duck and quacks like a duck, maybe it's a holographic duck.
And there was a note about time. We talked about space being emergent. What about time?
That is the next great frontier, the time problem. In the bulk, in the soup, time flows normally forward. But on the boundary, time behaves very differently. It's part of the quantum field itself. Reconciling bulk time with boundary time is extremely difficult.
So time might be an illusion, too.
It's very possible that time is also emergent. The past and future are just useful patterns in the entanglement on the boundary.
Great. Just what I needed. Time isn't real. Space isn't real. I'm a credit card sticker.
Chuckles. It's the price of admission for playing with modern physics.
So let's bring this home. Let's recap the journey, because we have covered a lot of ground.
We started with the library, with this bizarre realization that the capacity of the universe is written on the walls, not in the volume.
The beacon steam bound.
We moved to the soup can, the Maldacena conjecture, the mathematical proof that a 3D gravitational world can be identical to a 2D quantum world.
The dictionary. The cheat code.
We used that code to solve the information paradox, to save the diary from the black hole by smearing it on the event horizon.
And we ended up with this incredible idea that space itself is stitched together by quantum entanglement, that we're living inside a giant error-correcting quantum computer.
It really does change how you look at the world.
It does. It makes me feel lighter, or maybe just less solid.
It should make you feel connected. If space is just entanglement, then connection is the most fundamental building block of reality. We aren't just separate objects floating in a void. We're an interconnected web.
That's a beautiful way to put it.
And remember, the Wittgenstein bound implies we are finite. We are complex, yes, but we are limited. We are a finite amount of data that is, in a way, processing itself.
And I want to leave the listener with one final thought, one last provocation.
Go for it.
We keep talking about the screen, the boundary, the hologram. But a hologram is meant to be seen. An image is meant to be observed.
Yes.
If the universe is a projection, who is the audience?
What if we are the audience?
If we are the code, but we are also the ones studying the code.
Then the universe is waking up and looking at itself.
Yeah.
We are the mechanism by which the hologram understands that it is a hologram.
That is the ultimate loop.
It is.
On that note, I think I'm going to go touch my desk again and try to convince myself it's solid.
Good luck with that.
Thank you so much for guiding us through the soup can. This was fascinating.
My pleasure. It was fun.
And to everyone listening, next time you look up at the night sky, just remember, you might be looking at the ultimate projection screen. Thanks for joining us on this exploration. We'll see you next time.